Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here. It's just a quick introductory video on how to work just basic problems about AC voltage. So what we're going to do here is we're going to pretend that this 20 ohm light bulb is plugged into a US AC power voltage source. So the first thing we want to do is draw a circuit diagram. And just like with DC circuits, AC circuits have a symbol for voltage. And this round thing with a squiggly in the middle is the symbol for an AC voltage source. And then, just like with DC, this little sawtooth looking thing will represent the resistance of our bulb. So that's R equals 20 volts. And I'll go ahead and write over here that our voltage is equal to 120 volts, and again, that is an RMS voltage. Remember, the peak voltage in the US power grid is about 170 volts, but for calculations, we always want to use the average voltage, or the RMS voltage, which is the 120. Now, you've seen a lot of my videos on how I tend to like to handle circuit problems. You see me do a lot of color coding. I'm going to go ahead and do that here. The voltage, in our picture here, see, this is all conducting material in theory. This is a wire. And that means that this is an equipotential to here. Now, the voltage there is changing. Like sometimes on the curve, this voltage might be 120, sometimes it might be 60, sometimes it might be 10. But at any given time, whatever the voltage is here, it's the same here, it's the same here, because this is all conducting material. Same thing on the other side. And what that means physically for our problem here is that if the average voltage is 120 volts, black to orange, again, then I look at my light bulb, black to orange, that's the same voltage there. So long story short, all we need to do is apply Ohm's law, which hopefully we remember is voltage equals current times resistance. And I'm remembering now, I think I forgot in my previous video, but generally speaking, we like to use little I and little v for AC voltage problems as opposed to large I and large V. In this example, the RMS voltage is 120 volts because it's an AC voltage source in the United States. Current we're going to know in a moment. The resistance is 20 ohms. Whoops. Okay. This can be solved for the current easy enough. If we take 120 volts divided by 20 ohms, we get 6 volts per ohm. And it's pretty easy to show that that's equal to 6 amps. Now what have we found? We have found the RMS current. If we were to graph the current in this problem, similar to the voltage, the current against time is going to be a sine wave. It'll be sinusoidal. The peak here is what I would call the max current, and that's not the 0.6, or that's not the 6 amps. In a similar sense to the relationship between RMS voltage and RMS current, right? The max current you get by taking square root of 2 times the RMS value of 6 amps. Actual number here not important. I was just pointing that out for the graph. If we were to graph it, the peak of this graph is going to be whatever this is. Okay, now to find the power, now there's a couple ways we can do it. Power is equal to current squared times resistance. So we can take our RMS current, 6 amps, squared times 20 volts. And we get 36 times 20. And the units will work out to amp squared volt. And that will work out to watts. Oops. There's the 20. Thing didn't write it down. And if we work this out, what does this come out to? Let's see, 7200, 7200 watts, or 7.2 kilowatt. So there's the power of our source here. I always like to kind of put things in context. Electrical power right now in my part of the country, about the time I'm making this video, is running about, I would say, about 16 cents per kilowatt hour. So let's talk about, what is the context here. if we ran this for, say, 10 hours, or let's just make it 1 hour, that would be 7.2 kilowatt hour. And then the cost would be 7.2 times this 16 cents per kilowatt hour. And we're getting, a fairly large number there, probably, over, well, let me back up, relatively large compared to a light bulb. Well, our light bulb here, 7,200 watts is an awfully bright bulb. Most of the bulbs you buy are like 60-watt light bulbs. Now, why did this occur like this? I just made this problem up off the top of my head here. So I picked a resistance here that just was, relatively low. But the mechanics of how you work out the problem are all valid. So this is just meant to be example number 1 of an AC circuit type of power problem. I hope that this helps. Have a great day.